Hello, we are Team 4 consisting of these 3 members. I'm the first presenter, Jungmin Bae, and I will talk about the topic and related words of this project. Then Jin will present the paper overview. Lastly, Myung-ha will explain our replication plan and how we will improve the paper. The paper we will target in this project is self-supervised policy adaptation during deployment. We choose this paper because it was a spotlight presentation at ICERA 2021, and we think the topic of this paper is important and the solution is interesting. The problem topic targeted in this paper is a police trained in one environment might not generalize to other new environments. As you can see in the video, even if a police is well trained, it can fail in the test if the environment changes. This problem can be also applied to sim-to-real. The sim-to-real is already a difficult problem because of the gap between them. However, it can be more challenging if the real environment has a different environment from the simulation. As you can see in the video, generalization across different environments is hard even though the change is trivial. Then, how can we solve this problem? One approach for it can be to generalize a policy across different distributions or environments. For it, in domain adaptation, a policy learns target domains during training, assuming that the target can be accessible. However, of course, unexpected domains can happen in a real environment. So another method, domain randomization, is randomizing learning domains during training, assuming that the target can be one of the various environments learned during training. In this case, learning from an environment with large distribution can make policy optimization to be difficult. Moreover, too much randomization can reduce sample efficiency. Instead of learning a robust policy for all possible environmental changes like this, it can be better for a policy to keep learning in a new environment. The second approach, self-supervised learning, can be used to keep learning in new environment. This is a powerful way to learn in unlabeled data by creating supervision on its own and learning from it. Regarding it, like this paper, there are previous works that applied self-supervision for better generalization, and most of them use the rewards as the supervision in new environment. However, sufficient reward may not be available, and it may require substantial engineering efforts in the real environment. Thus, assuming that there is a reward in a real environment can bring limitations to generalization. The most similar approach to the method in the paper is the third approach, test time adaptation. It makes a model to adapt the given parameters and target data during testing. There are some studies regarding it, such as these 2 papers. However, this approach has been mainly conducted in computer vision. In this paper, the authors overcame the limitations of existing methods and expanded the concept of test time adaptation to reinforcement learning to adapt pre-trained policies to new environments, even without any prior data and assuming access to a reward signal. The next presenter will explain how this goal could be achieved in this paper.
I will summarize the PAD method proposed in this paper here. First of all, it learns a policy in a single training environment and deploys the policy in a target test environment. And then it adapts the policy during deployment itself. As you mentioned before, PAD does not require data prior to deployment, nor does it assume to access the reward signal at test time. This can be done by introducing self-supervision to obtain not reward signal but free training signal during deployment. In other words, PAD only uses data collected during deployment and adapts online using a self-supervised signal. The PAD algorithm consists of 2 phases. One is the initial training phase in a fixed environment, and the other is the adaptation phase during deployment in the target environment. In network architecture, one can think of phi-E as a feature extractor, phi A as a controller based on these features, and phi S as a self-supervised prediction model on the feature spaces. During training, there are signals from both the reward and self-supervised task, so policy is jointly trained by optimizing the RL and self-supervised objectives. However, in the adaptation phase, only the self-supervised objective remain active since the reward signal is unavailable. So observations are collected from the test environment online and adapt policy with optimizing only the self-supervised objective during deployment. In detail, PAD works as follows during the deployment. In a new environment, it takes an action at each step, observe the environment, then perform data augmentation, and finally update policy using the observation from the current step. This process is consecutively repeated. Through this process, PAD updates phi E during test time using gradient from a self-supervised task, so that phi E can generalize. In this paper, two different self-supervised tasks are considered. First one is that it learns an inverse dynamic model. It takes the states before and after transition and predicts the action in between. So it is useful for tasks that require motor control. And the other one adopts a rotation prediction task. An observation is rotated by one of four different angles and casts this as a four-way classification. So it is more suitable for tasks that require scene understanding, such as navigation tasks. In simulation, PAD is evaluated on continuous control tasks from the DeepMind control suite, as well as CRL-based navigation tasks. In this slide, the figure represents the experiment that transferred the learned policy to the stationary environment that differs in color. Next, researchers also evaluate generalization to diverse video background in non-stationary environment. PAD outperformed the other methods on most tasks in both environments and is relatively unaffected by the change of color or background. Results also show that PAD transferred from simulation to a real robot and is successfully adapted to environments difference during deployment in two robotic manipulation tasks, even in the presence of disco light and the tablecloth.
Next, let me tell you about our replication plan. We'll replicate model training and experimental results while referring to original paper's code and results. As in the paper, we will experiment the following two set of environments. In DeepMind control environments, a model will be tested on 9 continuous control tasks, such as standing worker, balancing cutable, and spinning finger. At this time, to verify the generalization performance, 4 types of test environments will be considered, such as randomized colors and videos background. For Chromase, a model will be tested on 3D navigation task or Vizdom. In the case of this task as well, 4 types of test environments will be considered, such as changing textures and lighting. In the replication and improvement step, we will experiment and simulate these environments. These are the experimental results of the paper. We will focus on the replication of these two PAD models, which show the best performance for each set of environments. This is our schedule for the replication. We plan to finish the replication before progress presentation. Since we don't have much time, we will proceed with both sets of environments in parallel. Unfortunately, in the case of Chromase, there is no code for PAD simulation. Therefore, we thought it will take a little more time. Our main approach for improvement is self-supervised learning with other tasks. In the paper, inverse dynamics and rotation prediction are used as self-supervised learning tasks. We would like to improve the performance of PAD by modifying these tasks or introducing a new self-supervised learning task, which is more suitable for a target task. In our main paper, rotation prediction is performed with a single rotated image by a randomly selected angle. However, according to the alternate paper that first proposed this task for image representation, feeding all the 4 rotated images to a model simultaneously is more helpful. We think replicating this will help our project. Next, the existing study we are currently considering to introduce a new task is SimClue. In this paper, 3 types of data augmentation are considered. Using transformed images, SimColor learns features through the contrastive learning, which is the new paradigm of self-supervised learning. Loss function of SimColor maximize similarity between transformed views of the same image and minimize similarity between transformed views of different images. In the case of the rotation prediction, loss is calculated according to classification output, and features are used for loss calculation indirectly. On the other hand, for SimColor, the features themselves affect loss calculation. Thanks to this approach, SimColor can learn better representation and show better performance than rotation method. We think applying this test to PAD will be also helpful. However, for constructive learning, a data pool of some size is required for learning. Therefore, in order to apply this task, we should modify the task to a suitable form for self-supervised learning of PAD. We will design and find an appropriate method throughout the project. Next is our references. Thank you for listening.